In this video, we want to continue on with our examples of autonomous first-order ordinary differential equations. And to solve this problem, again, what are we trying to do? We're trying to find out our solution x. So we're trying to find that function x of t. And in fact, what we're going to do is we're going to find what all solutions will look like and draw that out. So first, to do that, we want to factor this dx dt. And so what is this equal to? Turns out this is equal to negative x times x plus 1. Again, we're just factoring, times x minus 1 squared. So we just factored that solution to get negative x times x plus 1 times x minus 1 squared. Well, we can answer part 1 already now, finding all equilibrium solutions. Well, that is x equals 0, x equals negative 1, and x equals positive 1. And then to do parts 2 and 3, we first want to draw out our phase line. So what is that? Well, to draw the phase line, we want to just draw dx dt. We want to draw that function. So let's do that. And we're going to do that on the x comma f of x plane, f of x being dx dt. All right, we're just going to draw that. We have a fourth order polynomial. So a polynomial of degree 4 is what I mean there. Our points that intersect with the x-axis are negative 1, 0, and 1. And because our leading coefficient is negative, the end behavior should be pointing down here. And we have a double root at x equals 1. So our our function should look like this. All right. So we get that as our solution. Okay. So what does this tell us? So let's write down what this means about the phase line. Well, our function dx dt is negative on the region to the left of x equals negative 1. So that tells us the function x should be decreasing. So I'm going to draw an arrow to the left there, draw an arrow to the right here, and left here. And so we're going to rotate this line vertically for our phase line. We'll write in our x equals negative 1, x equals 0, and x equals positive 1 here. Let's draw in our tx plane and our actual solutions to the differential equation will be drawn in on this tx plane. We have 3 equilibrium solutions. So let's draw those now. And then we can draw our non-equilibrium solutions based on this phase line. And recall, if we rotate that phase line to this vertical phase line here, so from here to here, we're rotating. Then those arrows tell us what our x should be doing on these regions. So I'm going to input those arrows now as well. And they should rotate in those directions, into those directions. And this tells us what our non-equilibrium solutions do on these regions. And so we'll draw those in now. Okay, so we've really finished part 2 here at this point. We can also write part 3 just based on this information, and that is that our function is increasing on -1 to 0. We can use either the phase line or just look at the graph here that we just drew out to show that. And it is decreasing on all of the other intervals. So that would be -infinity to -1, union 0 to 1, union 1 to infinity. So that's the answer to part 3. That is the intervals on which our function x is, our non-equilibrium solutions are increasing or decreasing. And furthermore, we can answer part 4 here on which of these equilibrium solutions are stable, unstable, or semi-stable. This is for x equals -1. This is unstable because our solutions move away from that point. X equals 0 is stable because all solutions move towards that point. And x equals 1 is semi-stable because from one direction we move towards that equilibrium point, from the other direction, namely below, we move away from that equilibrium point. All right, so this fully solves our question on this autonomous first order ordinary differential equation. And again, what does that do? This really tells us what all possible solutions will look like, which is really nice to be able to do. All right, so that'll end this video here.